Hi everybody, Mrs. Pesic here. We're looking at section 4.3, right triangle trigonometry. In section 4.2, we look at the trig functions from a unit circle perspective. In section 4.3, we look at the 6 trig functions from a right triangle point of view. So the 6 trig functions are sine, cosine, tangent, cosecant, secant, and cotangent. We abbreviate all 6 of these trig functions with 3 letters. So the abbreviation for sine is always S-I-N, but it's just pronounced sine, not sin. The abbreviation for cosine is C-O-S, but again, when you see that, we say cosine, we don't say cos. All right? The abbreviation for tangent is T-A-N, but we say tangent. The abbreviation for cosecant is C-S-C, but again, when you see that, you'll say cosecant. When you see SEC, that's the abbreviation for secant, and you say secant, and the abbreviation for cotangent is COT, but again, you would say cotangent. So what's all this have to do with right triangles? If you have a right triangle, then you have one right angle, and you have 2 angles that are acute angles. So you can call, let's call one of them theta, so let's put theta there. That means that one of the sides of the triangle is the hypotenuse, one is going to be the adjacent leg, and one is going to be the opposite leg. So we know that the side opposite the right angle is going to be the hypotenuse, so that goes there. We know that the side opposite our angle theta would have to be over here, and that means that this side over here must be the adjacent leg. So we have an opposite leg, an adjacent leg, and a hypotenuse. Okay, if I switch and I put my theta here, well, the hypotenuse is not going to change, but then this would become the opposite leg, and this would become the adjacent leg. All right, let's go back to this way, though, that I had it originally. So opposite leg is across from the angle, and the adjacent leg is the one that has one side of that angle. All right, so how are we relating these trig functions? Well, the sine of theta is going to be the opposite leg divided by the hypotenuse. Okay, the cosine of our angle theta is going to be the adjacent leg divided by the hypotenuse. And the tangent is going to be the opposite leg divided by the adjacent leg. All right, and those might be kind of hard to remember, but maybe not if you just have this little mnemonic device, SO, CA, TOA. The SOH part right here is representing that the sine is the opposite over the hypotenuse, SOH. And the cosine, the CAH part, would be for the cosine is the adjacent over the hypotenuse. And then the tangent, the TOA part, means that the tangent, T for tangent, is the opposite over the adjacent. All right, so that SO, CA, TOA is a way to remember the angle relationships with a right triangle. Now, what about these other 3 trig functions, cosecant, secant, and cotangent? Well, cosecant is just the reciprocal of sine. So sine and cosecant are reciprocals. That means that the cosecant of theta is going to be the hypotenuse divided by the opposite. So if we know those lengths, we can divide them and get the cosecant of the angle in question. And the secant is the reciprocal of cosine. So we can write secant as hypotenuse over adjacent. And cotangent is the reciprocal of tangent, and so that means that we can write this as adjacent over opposite. All right, so those are your trig functions for a right triangle. Let's see how to use those in practice here. So let's try this example. We have a right triangle, and it's our favorite 3, 4, 5 right triangle. And so if we want to find the sine of that angle, I don't have an angle picked yet. Let's make this our angle theta in question. So if this is our angle, then which side is our hypotenuse, which side is our adjacent leg, and which side is our opposite leg? Well, 5 is going to be the hypotenuse. 4 is going to have to be across from it, so 4 is the opposite leg, and 3 is the adjacent leg. All right? And so now if I want to find the sine of this angle theta, I need the opposite, remember SO, CA, TOA, spelling counts here. So SOHCAHTOA, we need the sine is the opposite, which is 4, over the hypotenuse, which is 5. Let me write this out a little bit more. So sine is the opposite over the hypotenuse, so that would be 4 over 5. How about the cosine? Cosine is going to be adjacent over hypotenuse, right? CAH. And so that's going to be 3 over 5. And the tangent is going to be the opposite over adjacent. And that's going to be 4 over 3. All right, that's how you would find the cosine, sine, and tangent if you know the 3 sides of a right triangle. Let's try this example. We're finding the 6 trig functions of theta in this picture. All right, we're going to find all 6 this time, so we want to find sine, cosine, tangent, cosecant, secant, and cotangent. So in order to find the trig functions, we are going to need to find this side. We don't have a length there, but it is a right triangle, so we could use, Pythagorean theorem. If we call this side x, for example, it's one of the legs, and this side here is another leg. So we can write x squared plus 12 squared equals 13 squared. And if you work that out, I think that you end up getting x squared equaling 25, and we take the square root, and we get x equaling plus or minus 5. Well, we're going to take positive 5 for the side length, and so this side has to be 5. Now we can go about finding the 6 trig functions of this angle right here. So before we do that, maybe we should write in that 13 is the hypotenuse. And which side is the opposite side from this angle? Well, that would be 12. That's going to be opposite. And 5 is going to be the adjacent leg, or the adjacent side. All right, so to find the sine, that's opposite over hypotenuse. So that's going to be 12 thirteenths. And the cosine is the adjacent over the hypotenuse. So that's going to be 5 thirteenths. And the tangent is the opposite over adjacent. And so that's going to be 12 fifths. And remember, the cosecant is the reciprocal of sine. So that means this is just going to be 13 twelfths. Secant is the reciprocal of cosine. So that's going to be 13 fifths. And cotangent is the reciprocal of tangent. So that's going to be 5 twelfths. All right. Let's take a look at another example. This one says, without using a calculator, can you find the following? So the sine of 45 degrees, the tangent of 45 degrees, sine of 30, cosine of 60, and so on. This is going to require us to recall our special right triangles. Remember, the 45-45-90 triangle and the 30-60-90 triangle are referred to as special right triangles because you really only need to know one side and you can find the other 2. Whereas with any other right triangle, you need to know 2 sides to find that last side. All right, but if I can remind you or inform you that in a 45-45 right triangle, if the 2 angles are congruent, that means these 2 legs are going to be congruent. So if, for example, this leg right here had a length of 1, then this leg here is also going to have a length of 1. And we could use Pythagorean theorem and find the hypotenuse. 1 squared plus 1 squared equals x squared. That's 1 plus 1 equals x squared. 2 equals x squared. Take the square root and we get x equaling the square root of 2. So that's how we get this as our hypotenuse. Okay? So now that we know all of that, then we can use our SOHCAHTOA rules to help us find these trig functions. So if I pick this 45-degree angle, for example, then this is the hypotenuse. This side would be the opposite side, and this side would be the adjacent side. Really doesn't matter. I could have picked the other 45. It's all going to be the same. Okay, and then so the sine of 45 degrees is going to be opposite over hypotenuse. So that's 1 over square root of 2. But let's not leave radical in the denominator. Let's multiply by rad 2 over rad 2. So we get square root of 2 over 2. So that's what we should be writing here for square root of 2 over 2. I think the cosine is going to end up being the same way, because then we're going to want the adjacent leg divided by the hypotenuse, but it's still going to be 1 divided by square root of 2, and that's still going to end up being square root of 2 over 2. So whoops, down here. So that's cosine is also going to be square root of 2 over 2. Well, what about the tangent? The tangent is the opposite over the adjacent. Well, in this case, it's just 1 over 1 is 1. So the tangent of 45 degrees is just equal to 1. All right, let's switch gears and look at a 30, 60, 90 triangle. So let me clear out some of this stuff here. And the rule with 30, 60, 90 triangles is that the hypotenuse, which would be this leg right here, is always going to be double the short leg. And the short leg is the one that's across from the 30-degree angle. So this is the short leg, this is the long leg, and this is the hypotenuse. All right, so for the short leg, if the short leg is 1, then the hypotenuse is going to be double that, and that's going to be 2. And then how do we find the long leg? Well, that's always short leg times square root of 3. So really 1 times square root of 3, but that's just equal to square root of 3. So now that we've kind of talked about how we get the side lengths in a 30, 60, 90, now that we know these lengths could be 1, 2, and square root of 3, let's find the sine of 30 degrees. So I'm going to focus on this 30-degree angle here. The sine is going to be opposite over hypotenuse. And so this opposite, 1 is going to be the opposite side, square root of 3 is the adjacent side, 2 is the hypotenuse. So if I want opposite over hypotenuse, I want 1 over 2. So the sine of 30 degrees is going to be 1/2. How about the cosine of 30? Well, the cosine of 30 is going to be the adjacent over hypotenuse. That's going to be the cosine. And so adjacent is going to be square root of 3 over 2. Adjacent is square root of 3, hypotenuse is 2. And we're just going to leave our answer like that. So the cosine of 30 degrees is square root of 3 over 2. How about the tangent? The tangent of 30 degrees is going to be opposite over adjacent. And so in this case, opposite side is going to be 1, adjacent side is square root of 3. But let's not leave it as 1 over square root of 3. Let's multiply by square root of 3 over square root of 3. So we end up getting square root of 3 over 3 as our tangent. All right, let's switch gears now and talk about the trig functions for the 60-degree angle. All right, so in this case, clearing things off here. So this now means we're going to be focusing on this 60-degree angle. That means that the square root of 3 is now going to be my opposite leg, and 1 is going to be my adjacent leg. 2 is still going to be the hypotenuse. And so the sine of 60 is going to be opposite over hypotenuse. So in this case, that would be square root of 3 over 2. So that's our sine of 60 degrees, square root of 3 over 2. What about the cosine of 60? Cosine of 60 is going to be equal to the adjacent over the hypotenuse. And so in this case, that's going to be 1 over 2. So cosine of 60 is 1/2. And how about the tangent of 60? Tangent of 60, tangent of 60 degrees is going to be the opposite over the adjacent. And so in this case, that's going to be square root of 3 over 1, which is just square root of 3. All right, now I want you to notice something, and that is that the sine of 30 degrees is the same as the cosine of 60, and the cosine of 30 is the same as the sine of 60. And that's always going to happen. That relationship is always going to happen. So we kind of talk about that. Notice that the sine of 30 is equal to cosine of 60. That's always going to happen with complementary angles. 30 and 60 are complementary, and sine and cosine are co-functions of each other. So the rule is that the co-functions of complementary angles are going to be equal to each other. So for example, the sine of 70 degrees is going to be equal to the what? Well, it's going to be the cofunction. It's going to be cosine instead of sine, cosine. And the complement of 70 degrees is 20 degrees. So the sine of 70 degrees is going to be equal to the cosine of 20 degrees. How about this example? Cosecant of 40 degrees is equal to what of what? Well, we need the cofunction of cosecant. So either add the co or drop the co. In this case, if we drop the co for cosecant, we get secant. That's SEC. So secant of, and we need the complement of 40 degrees, which would be 50 degrees. So the cosecant of 40 is always going to be equal to the secant of 50. In general, we can, summarize this with these statements. So if we have sine of 90 minus theta degrees, that's going to be equal to what? Well, the cofunction of sine is cosine, and the complement of 90 minus theta would be theta, right? Because if I add theta and 90 minus theta, I will get 90 degrees, right? So those are complementary angles. So, so the cosine of 90 minus theta is going to equal the sine of theta. The tangent of 90 minus theta is going to be the cotangent of theta. And the cosecant of 90 minus theta is going to be the secant of theta. Again, I'm just either throwing the word co on, or I'm taking the, the prefix co off to get the cofunctions, and then I'm saying 90 minus theta and theta are complementary angles. So secant of 90 minus theta is going to be the cosecant of theta, and the cotangent of 90 minus theta is going to be the tangent of theta. So I think these examples up here kind of maybe are a little easier to follow, but in general we can say that 90 minus theta and theta are complementary angles. All right, let's move on from that and talk about trig identities. A trig identity is a relationship between trig functions, and there are some fundamental identities that you will need to memorize. All right, the reciprocal identities, we already kind of talked about this a little bit, that for the reciprocal identity, sine is the reciprocal of cosecant. That means that sine is equal to 1 over cosecant, and likewise cosecant would be 1 over sine. Those are reciprocals of each other. Cosine and secant are reciprocals, so cosine is going to be 1 over secant of theta, and secant is going to be 1 over the cosine of theta. Tangent and cotangent are reciprocals of each other, so tangent is going to be 1 over cotangent of theta, and cotangent of theta is going to be 1 over tangent of theta. All right, and that brings up our next, so those are all reciprocal identities. And the next type of identity that we want to study would be the quotient identities. So the tangent of theta is always going to be equal to the sine of theta divided by the cosine of theta. The quotient of sine over cosine is going to be equal to tangent. And since tangent and cotangent are reciprocals, cotangent of theta could be expressed as the cosine of theta divided by the sine of theta. Those are the two quotient identities. All right, we have 3 more fundamental identities to learn. So we've had the reciprocal identities now, we've had the quotient identities, and the last 3 are considered Pythagorean identities, and they look like this. So the first one is sine squared theta plus cosine squared theta is always going to be equal to 1. All right. And when we write sine with a little 2 like that and squared, that really means sine of theta quantity squared. But mathematicians don't write sine of theta in parentheses and put squared on the outside like this. Instead, they write it like this. They just write sine squared theta, but it means take your sine of theta and square it. All right, so that's like our little abbreviation for sine of theta quantity squared. We'll just write sine squared theta. So that's our first Pythagorean identity right here. Another one is 1 plus tangent squared theta is always going to be equal to secant squared theta. And the last Pythagorean identity is 1 plus cotangent squared theta is equal to cosecant squared theta. All right, so those are our three Pythagorean identities. Okay, so these fundamental identities, you will need to memorize them, and I am going to suggest that you write these on little flashcards, like put, one side on one and what it's equal to on the other side, but we'll talk about that to help you learn these. Okay, so let's take a look at this example. Let theta be an acute angle such that cosine of theta is equal to 0.96. And we are trying to find the values of the following by using trig identities. So let's find the sine of theta. Well, which trig identity are we going to use? It says using trig identities. Well, if we know cosine of theta and we're trying to find sine of theta, what's the only trig identity that we see here that involves just sine and cosine? Not this one, because this one has sine, cosine, and tangent in it, so that one's no good. But I think this one is the one we want right here. Sine squared theta plus cosine squared theta equals 1. It's the only trig identity that only involves those two trig functions. So let's use that one. We're going to write sine squared theta plus cosine squared theta is equal to 1. We're going to plug in 0.96 for cosine right here, 0.96. But remember, that has to be squared because it was cosine squared. So we get sine squared theta plus the 0.96 quantity squared equals 1. And let's grab our calculators to find out what is 0.96 squared. So if I do 0.96 squared, I get 0.9216. 0.9216 plus sine squared theta has to equal 1. So if I subtract 0.9216 from both sides, I end up getting sine squared theta equaling what? I need 1 minus 0.9216. So 1 minus my answer, control negative sign, 1 minus my answer, I get 0.0784. 0.0784, and that's sine squared, but I want to find sine, so I'm going to take the square root of both sides. And when I get the square root of that number, going back to my calculator, the square root of that answer, and I'm getting 0.28. So sine of theta is going to equal 0.28. So that's our answer for part A. For part B, you're asked to find the tangent of theta. Well, which trig function involves sine, cosine, and tangent? Because now we've got sine to use as well. Let's go back here. Which trig function involves sine, cosine, and tangent? This time, this is the one that we want here. So we're going to write tangent theta equals sine theta over cosine theta. So tangent theta equals sine theta divided by cosine of theta. So that means I want 0.28 divided by 0.96 was the cosine that was given. So on our calculator, we're doing 0.28 divided by 0.96. There's my 0.28 divided by 0.96. I'm getting 0.2917 approximately. I'll go with that, 0.2917. 0.2917. That's going to be our value for tangent. All right, let's take a look at another example. Use trig identities to transform one side of the equation into the other side. Note, we're talking about an angle in the first quadrant. So theta is between 0 and pi over 2. All right, so this is our first look at how to verify a trig identity. And we get just a small taste of it in section 4.3, and we get a whole banquet of it in chapter 5. But let's take a look at this. We're trying to rewrite, let's say we're trying to rewrite the right side of the equation so it ends up looking like the left side. So let's leave the left side alone, and we can rewrite 1 over sine squared as 1 over sine theta times 1 over sine theta. Right? Sine squared means sine times sine. But what is 1 over sine theta? That's one of our identities. If you're looking back at what you've written, hopefully 1 over sine theta is equal to cosecant theta. So I have cosecant theta times cosecant theta minus 1. And again, I'm trying to show that this is equal to cotangent squared theta. Well, cosecant theta times cosecant theta could be written cosecant squared theta minus 1. Right? And is that one of our identities? I don't think so, but let's go back here to our identities for a minute. It looks awfully close to this one right here. It's got cotangent and cotangents and cosecants in it. Well, if cosecant squared is equal to 1 plus cotangent squared, then I can rewrite my cosecant squared just like that. So I can rewrite cosecant squared as 1 plus cotangent squared theta. And then I've got this minus 1. And again, I'm trying to show that this is equal to cotangent squared theta. And now I really do see that my 1's could subtract off. And so I end up getting cotangent squared theta is equal to cotangent squared theta. So we've shown that we can manipulate this right side until it looks just like the left side. All right, so that's an example of verifying trig identities. So we get a lot more of this in sections 5.1 and 5.2 once we get there. All right, let's take a look at this. Use your calculator to evaluate the secant of 5 degrees, 40 minutes, 12 seconds. Let's make sure we can do this on our calculator. So 5, 40, and 12. So if I go here and I want secant, I'm going to push the trig button, and I'm going to go to secant, and I want 5 degrees, 40 minutes, and 12 seconds. So remember, I got to do that minute button twice. Is that correct? 5, 40, 12, secant, yep. And so when I do that, I end up getting 1.00492 for my answer for that one. All right, and let's try cosecant of 34 degrees, 30 minutes, 36 seconds. So that is going to be trig button. Now we want cosecant of, it was 34, 30, 36, 34 degrees, 30 minutes, and 36 seconds. Was that right? 34, 30, 36. Yep. And so we are going to end up getting 1.76507 for that one. 1.76507. Right? Okay. And now let's talk about how we're going to see some of these SOHCAHTOA kind of problems in terms of a word problem. Well, they might be in the context of a problem where it's talking about an angle of elevation or an angle of depression. So an angle of elevation would be some kind of problem where there's some observer, could be you, and you're looking up at some object that's on a hill or up in the sky or something like that. And the angle of elevation is going to be this angle from the horizontal up. All right. Similarly, the angle of depression is going to be you or someone else as the observer, and you're looking down at something. So maybe you're on a hill and you're looking down at a boat on the water or something like that. But again, it's going to be angle from the horizontal down. That would be your angle of depression. All right, so let's take a look at this example. And this is not really an angle of depression or angle of elevation problem, but let's take a look. A 12-meter flagpole casts a 12-meter shadow as shown in the picture. So let's say here's the 12-meter flagpole, and let's say the sun is shining, and this is the shadow that's being cast, and that's also 12 meters, and we're supposed to find the angle of the sun. Well, I think this one doesn't really involve trig, maybe it does, but I hope you're noticing that if the two legs are equal, then in a right triangle, then this angle's got to be 45 degrees, and this angle is going to have to be 45 degrees also. So that would be our answer for that one, 45 degrees. right, let's take a look at this example. A biologist wants to know the width W of a river. Let's say here's the river going by here, and here's the width of the river, I'm calling it W. From point A, just gotta get this whole picture on here. From point A, the biologist walks downstream 70 feet. So let's say gets to this point B, for example, and then sights from it to across to point C, which was directly across from her starting point. Right, so we got a right angle here. From this sighting, should be capital F. From this sighting, it is determined that angle theta, that's her angle that she's measuring here, is 54 degrees. So we want to know how wide is the river. Well, we know that she walked 70 feet here, so this is 70, and we're trying to find the width W. So we know if this is angle is 54, the 70 would be the what? The hypotenuse, the adjacent, or the opposite? Well, that's going to be the adjacent leg. And the width, W, that we're trying to find would be the opposite leg. So which trig function involves opposite and adjacent? Think SOHCAHTOA. So that's going to have to be tangent. That's the opposite over the adjacent. So in this case, that means I can write tangent of 54 degrees is equal to W, that's my opposite side, over 70 was my adjacent side. So let's get tangent of 54 degrees on our calculators. I want trig tangent 54, and I gotta say degrees, and I am getting that equaling 1.376. I'll just go with that, 1.376. 76 is equal to W over 70, and now I can multiply both sides by 70 to get the width of the river. So if I multiply there by 70 on my calculator, so times 70, and I end up getting 96.34. Say 96.35. Oops. So let's say the width of the river is 96.35. Let's see, 96.35. And I think that was feet. Is that correct? Is that the unit that we were using? Yes. All right. So that's an example of a word problem using SOHCAHTOA. Let's take a look at another one. A ramp 17.5 feet in length rises to a loading platform. The angle that the ramp makes with the ground is 23 degrees. So here's our ramp here, and here's the angle that it makes, 23 degrees. And we want to find the height that the ramp reaches, and we know that the ramp itself is 17.5 feet, so we're looking for this height. All right, so we're looking for the height, which would be the what? Is that the adjacent leg, the opposite leg, or the hypotenuse? Well, that height is the opposite leg. And what about the 17.5? Is that the adjacent leg or the hypotenuse? Well, it's across from the right angle, so it's going to be the hypotenuse. So which trig function involves opposite and hypotenuse? That would be from SOHCAHTOA. That would be the sine is the opposite over hypotenuse. So we want the sine of 23 degrees equals h over 17.5. H for the height of the ramp, or height that the ramp reaches. So we need to do sine of 23 degrees and then multiply that by 17.5. So sine of 23 degrees is 0.3907. So 0.3907 equals h over 17.5. Let's multiply both sides by 17.5. And we end up getting what? Times 17.5. And we get 6.84. So about 6.84 feet height of the ramp 6.84 feet. All right. And that's it for this video. Thanks for watching.